Okay, here we go with Algebra 2, section 7.5. Okay. Alright, I can tell this is not going to work. So much for being safe. Just don't cough on me. Alright. Oh, what happened here? Well, it's supposed to say Algebra 2, section 7.5, part 1. And we're going to split this chapter into two parts. I'm all flustered. I've got all this junk laying around here. Man, who put this stuff in the way? All right, first of all, there was an error that, well, was there an error? Some of you may have caught something in the discussion of page 308. Was it an error, or was it not an error? So from the previous video, the discussion of page 308, let's take a look at number 14. And regarding number 14, yeah, also there's a similar story that can be told for number 50. So let's consider what the error might have been. Square root of x minus square root of y times square root of x plus square root of y. Alright, it's like a minus b times a plus b. We know how to do a minus b times a plus b. It's going to be a squared minus b squared. Alright, no problem. So it's going to be square root of x squared minus square root of y squared. So where's the error? Well, what's the square root of x squared? Haha! Yes, it should be absolute value of x. And what's the square root of y squared? It should be absolute value of y. Or, perhaps, it's not what's wrong with the previous answer. Maybe the question should be, what's right with the previous answer? What does absolute value do? It turns things positive, right? And that goes back to, I think it was the section 7.1 video. But something we already know about x and y. Go back to the original problem. Is x allowed to be negative here? Can we take the square root of a negative? No. Can we take the square root of a negative here either? No. Which means that in the original problem, x must already be positive. It's not allowed to be negative. Y must already be positive. Y is not allowed to be negative because we can't take the square root of a negative. So we already know, based on the original problem, that x and y are positive. If x and y are already known to be positive, why do we need to repositize them? We don't. They're already positive. So we don't need the absolute value. Now, if you're wondering, the answer in the book has absolute value. It doesn't hurt, but it's not necessary. So, what happened yesterday when I created this answer? Was I thinking about that? No, I wasn't. I simply forgot to consider absolute value. I just forgot. But it's one of those cases where you can mess up and forget something and get away with it because it turns out we really didn't need it anyway. So, what was wrong with it? We should have at least considered absolute value. What's right with it? We actually didn't need it because we already knew that x and y were positive. There's no need to make them positive again. All right, moving on. Section 7.5. What is the cubed root of 8 squared? Well, that would clearly be the cubed root of 64. The cubed root of 64. And by this time, you may have enough experience to immediately recognize what the cubed root of 64 is. If you don't immediately recognize it yet, come on, you need to do some practice on this stuff. Cube root of 64 is exactly 4. Now on the other hand, what if I move the exponent to the outside and make it the cube root of 8 to the second? What's the cube root of 8? 2. And what's 2 squared? 4. Just coincidence? Let's try another one like that. The square root of 4 squared. Well, what's 4 squared? 4 squared being 16. The square root of 16 is, of course, 4. What if we move the exponent to the outside? Here. What's the square root of 4? 2. What's 2 squared? 4. Coincidence? I think not. Here's the conclusion. This happens to be theorem 7.6 in the book. Being a theorem means it's provable using tricky algebraic techniques. It could be proved that this is true. We're not proving anything. We're simply demonstrating by examples that it appears to be true, but you can trust it. It is true. Theorem 7.6 says this, that the kth root of a to the m is indeed the same thing as the kth root of a to the m. In other words, it doesn't matter whether that m, let's break this up one moment, it doesn't matter whether that m is inside or outside. It means exactly the same thing. Now, by the way, most of the time, when I put an exponent outside the radical, I make it pretty clear that it's outside the radical, and I do not use parentheses. I've noticed that the book always uses parentheses. Sometimes I do when I'm trying to think like the book writers, and sometimes I don't. But please note that this means exactly the same thing as this. I just, most of the time, do not include the parentheses. Okay, so that is our general rule. Let's put it back the way theorem 7.6 is stated, that the kth root of a to the m is the same thing as the kth root of a all to the m. Some examples. How can this be used to your advantage? Well, here, the cube root of 27 to the second. Do we want to think of that as being the cube root of 27 squared, which is 729, and for that you either pull out a calculator if you know how to do cubed roots on the calculator, or you just spend 10 minutes trying to figure out what the cube root of 729 is. Oh, as I say here, yuck. Okay, you just don't want to go there. Is there an easier way? Well, yeah. Just take that silly little 2. Let's ungroup it first. Take that silly little 2 and move it outside. Think of it like this instead. What's the cube root of 27? Ooh, we know that one. That's 3. That becomes, get my ink back, that becomes 3 to the second, which is 9. Yeah, it does turn out that 9 times 9 times 9 is 729. But it's a lot easier to move the exponent to the outside, do this part first, and then square the answer. Much easier. Sometimes this is easier. Sometimes it's not. It's your choice. The next example here. Well, we could think of this as the cube root of 2 to the 6th. And there is a way to do it like that that's not too bad, and the book points it out to you. I would just refer you to the book. I'm not going to go through it because there is a much easier way. Because who knows what the cube root of 2 is? It's irrational. What a mess. So how about if we think of it like this instead? Leave the exponent inside where it started out. Leave it inside. 2 to the 6th. 2 times 2, 4. Times 2 again, 8. Times 2 again, 16. Times 2 again, 32. Times 2 again, 64. This is actually the cube root of 2 to the 6th, which is 64. And yes, we all know the cube root of 64 is simply 4. Much easier this way than to try to deal with it this way. So whether you decide to put the 6 inside or outside is up to you. Sometimes outside is easier, sometimes inside is easier. It's all the same thing. Which way is easier, you can decide for yourself on the spot. This guy. A couple ways to look at this. Here's the easiest way to think of this one. Isn't this the same thing as the square root of 5x squared times the square root of 5x? Square root of 5x times square root of 5x times square root of 5x. Square root of 5x times square root of 5x times square root of 5x. It's all the same thing. So what is the square root of 5x squared? Well, the square root of 5x squared is going to be simply 5x. Oh, what about absolute value? This time I don't need absolute value because... Oh, wait a minute. Do I? Oh, this gets tricky. Yes, I do need absolute value because we are indeed taking the square root of... Oh, no, I don't. Oh, this is interesting. In this form, x could be negative. No, it can't, because we still can't take the square root of a negative. So we know x is positive. We know x is positive. I was thinking wrong. I was thinking, never mind. Ignore what I was thinking. But because you can't take the square root of a negative, then x can't be negative. So we don't have to worry about absolute value. I don't remember if the book included absolute value in this answer or not. I do not recall. And this guy, nothing we can do with him. Bring him down, so there's your final result. There is a somewhat different way to look at this. Another way to examine the same problem would be to put the exponent inside like this. And I just made a very tragic mistake on purpose. What did I do wrong? The whole thing is to the third power. Therefore, inside, the whole thing must be to the third power, not just the x. Well, now, is not this the same thing as writing the square root of 5x squared times another 5x? Sure. A step which you would probably do in your head. In other words, back here, we have 5x to the third. This is the square root. Can we not simply take out 5x to the second? Can we not take out 5x to the second? Pa-ching! Pops out, becomes 5x. What's left inside? The other 5x is left inside. Hit pause and meditate on that for a few moments. All right, now consider this. A squared times a to the third. Yeah, now remember, from long ago, back in some way earlier chapter, my advice. When you can't remember one of the exponent rules, what do? The famous Peer quote. When in doubt, think about what it means. When in doubt, think about what it means. What does this mean? It means, this is review of way old stuff. This is a review of Algebra 1 stuff, actually. When in doubt, think about what it means. What does this mean? A times A times A times A times A. 1, 2, 3, 4, 5. That would be A to the fifth. Oh, of course, I remember now. When you're multiplying, that's why you add the exponents. It's A to the 2 plus 3. Of course. I forgot the rules, but I saved myself by thinking about what it means. It means A times A times A times A times A. That's A to the fifth. I can count. Yeah, so you know the old rule. When multiplying, you add the exponents. So if that's the case, when multiplying you add the exponents, then what would a to the 1/2 times a to the 1/2 be? It would be a to the 1/2 plus 1/2. Well, of course, 1/2 plus 1/2 is 1, which equals just plain a. I mean, do fractional exponents exist? Well, let's see. What is, on the other hand, the square root of a times the square root of a? We know from experience that that's going to be the square root of a squared. And we know that the square root and the square cancel, so square root of a times square root of a is just a. Assuming for a moment that a is positive. Well, a does have to be positive, so it's not an issue. Now, notice please that this equals a, and so does this equal a. If these both equal a, then these guys must equal each other. Which means that a to the 1/2 times a to the 1/2 must be the same as square root of a times square root of a. Which leads us to the definition, the meaning of a to the 1/2. A to the 1/2 means square root of a. So, quick example of that. What therefore would be 16 to the 1/2 power? 16 to the 1/2 power is 4. What's 100 to the 1/2 power? And don't you dare say 50. No. This means the square root of 100. So it equals 10. 36 to the 1/2 power equals 6, because 6 squared is 36. Now, if you happen to be thinking, that's the dumbest thing I've ever seen, I don't believe you. Well, if you know how to work with exponents on your calculator, try it on your calculator. For instance, go ahead and put in something like 25 to the 1/2. How do you do that? Well, one way to do that would be, there are multiple ways, but you could put in 25 to the 0.5. That's a 1/2 power, right? And you have a, by the way, on your calculator, where is the to the key? How do you do 25 to the anything? Depends on the calculator. Some calculators will have a key that says x to the y. You would hit 25, you would hit x to the y, and you would hit then 0.5. Other calculators have a to the key that looks like this. 25, then you hit this key. That means to the power of, to the 0.5. Guess what you're going to get? Well, what is the square root? What is 25 to the 1/2? What is the square root of 25? The calculator will give you an answer of 5. The calculator knows these rules as well as I do, and now as well as you do. So here's your rule. That a to the 1 over k equals the kth root of a. So the denominator here ends up being, what do you call that number there? Do you remember? It starts with I. Yeah, I heard you. Index. Yes, this is the index. The denominator becomes the index. Examples. The instructions in the book and the homework will say, write without rational exponents. On the Chapter 7 test, if we ever get there, we will, but it's going to be a while. We're only about halfway through the chapter, I think. Oh, big chapter. But if the instructions say to write without rational exponents, that simply means to change x to the 1/2 into the square root of x. Oh, but you said the denominator was the index. Oh, yes, that's right. If there's no index, it's automatically a 2. I see. Uh-huh. And of course, we don't normally put that 2 there. So what's 27 to the 1/3? 27 to the 1/3 would have to be the cubed root of 27, which is 3. Now on the homework, I would really, really hope that you would be able to go from here to there without having to show me the in-between step. Yes, sometimes shortcuts are encouraged. I would hope that you could say, oh, that just means the cubed root of 27. I know that one. It is 3. Yeah. Now watch out for this guy. ABC to the 1/5. We're going to keep it simple. Don't think complicated. Oh, that's so scary looking. No, it's not scary. All you're doing is following the instructions. You're going to write it without rational exponents. You're going to get rid of the fractional exponent. Oh, so all I have to do is write ABC? No. You have to write something equivalent to this, but without rational exponents. So the denominator becomes the index, and we have A, B, C inside. That's all. Keep it simple. Now watch out though. Just wanted to warn you. This is not the same thing as this. For this guy, the parentheses say the whole thing is to the 1/5 power. This one says only the C is to the 1/5 power. Remember your order of operations. Exponents are done first before multiplications. So this would be AB times the 5th root of C. Be careful about your order of operations. Parentheses do make a difference. Reversing the process. You're also going to see in the homework and on the test instructions that say something like write with rational exponents. So we just take the 7xy, and instead of the 5th root, we write it as a 1/5 power. That's all you do. You're done. Don't let this one mess with your mind. It looks ugly, but keep it simple. All we have to do is take x cubed y over 9. It's the 7th root, so it's to the 1/7 power. That's all they wanted you to do. But how do I know that's all they wanted? Well, did I just write it with rational exponents? Yes, I did. So did I follow the instructions? Yes, I did. I'm done. I have rewritten it from radical form into rational exponent form. Mr. I don't understand. What's the word rational all about? Oh, the word rational here? Oh, don't forget what a ratio is. It's just a fraction. This says to write it with fractional exponents. Ratios are fractions. Write it with fractional exponents. And the previous instructions said to write it without fractional exponents. Get rid of the fractions in the exponents. Write it in radical form instead. So this is called radical form. This would be rational exponent form. Rational exponent, radical form. The language of algebra. Okay, we did that. All right, so, oh yes. What then does a to the 2/3 power mean? Well, wouldn't that be the same thing as a to the 1/3 to the 2nd? Oh, I don't remember that rule. You know what to do when you don't remember a rule. Come on. When in doubt, remember what it means. How does one deal with, for instance, a to the 2nd to the 3rd? Well, I don't remember. Do I add? Do I multiply? What do I do with those exponents? Oh, come on. When in doubt, think about what it means. What does this mean? It means a squared times a squared times a squared, right? A squared to the 3rd power. What does that mean? A times a times a times a times a times a. Do I need to write that out? Okay. A times a times a times a times a times a. 1, 2, 3, 4, 5, 6. That's a to the 6th. Yes, indeed. Second time today, I can count. So can you. A to the 6th. Then you look back at the original problem and you say, oh, well, if that's going to end up being a to the 6th, I remember the rule now. The rule is all I have to do is go a to the 2 times 3, otherwise known as a to the 6th. Here's the expression to memorize, another peer quote. For a power of a power, multiply. For a power of a power, multiply the exponents. All right, that being the case, back here, what does a to the 2/3 mean? Well, it means a to the 1/3 to the 2nd, because what's 1/3 times 2? Oh, Mr. Peer, you're challenging us so much today. That's just elementary math. How do you do 1/3 times 2? You know all this stuff from back about 3rd grade. 1 times 2 is 2. 3 times 1 is 3. So, yes, 2/3 is 1/3 times 2. Correct? Correct. So what does this mean then? Well, the 1/3, the 3 down here, becomes your index. Remember the old rule from how far back? 1, 2, 3, right there. That your denominator becomes your index. That being the case, if your denominator becomes the index, then we have the cubed root of a inside the parentheses. And it's still to the 2nd power. Or, remember, if we wanted to, we could move that 2 to the inside like this. Either way is fine. So what does that imply? It appears that, going back to the original and comparing to this, when changing this into radical form, the denominator became the index, the numerator became the power. And it doesn't matter whether you put the power outside or inside. The denominator became the index, the numerator became the power. You have to memorize that. Oops, that's where we were before. Here's the rule. A to the m over k. The denominator becomes your index. The numerator becomes the power, whether on the inside or on the outside, does not matter. The denominator becomes the index. The numerator becomes the power, inside or outside, your choice. All right, so here, the instructions in the book and the instructions on the test will say write without rational exponents. Get rid of the rational exponent. So this becomes, remember, the denominator becomes your index. The the numerator becomes your exponent. Inside or outside, well, we know from experience this one we want to put on the outside. Cubed root of 27? 3. 3 squared? 9. Again, I would hope that you could jump straight from here to here by saying to yourself, well, the cubed root of 27 is 3, and then 3 squared is 9. Oh, yes, I almost forgot here. How could I with this? There is a mistake in the book. Example 10 on page 312. They made a little mistake there, a little very important mistake. A silly little careless typo. See if you can find it. I'm not going to tell you what the mistake was. See if you can find it. But a rather, I think, blatant, obvious, silly error on their part. So see if you can find the mistake in example 10 on page 312. Always fun to find book writers' mistakes. All right, so this guy. Hey, we can do it the long way or the hard way. Let's do this one the long way. By long way, what I mean is this. It's going to be a radical. The denominator becomes the index. Well, I don't need to put a 2 here, do I? and the numerator becomes the power. And there we go. So what's the square root of 4? 2. And then 2 cubed is 8. Okay, let's do this one the short way. What's the cubed root of 8? I'll give you 4.5 seconds. Yep, it's going to be 2. And then 2 squared is 4. Want to see that the long way, just for clarity? Okay, fine. This becomes the cubed root of 8 squared. The denominator becomes the index. The numerator becomes the power. That's it. This becomes 2 squared, which is 4. Or if you prefer, hey, go ahead and put the 2 on the inside for all I care. That gives us cubed root of 64, and we know the cubed root of 64 is 4. Same answer, of course. This time, we are told in the instructions to write it with rational exponents. In other words, get rid of the radical and replace it with a fractional exponent. This would be 8 to the, now remember, the rule is easy. The index becomes what? It becomes the denominator, so we put a 3 down here. And the power becomes the numerator. We're done. 8 to the 4/3. That's all they wanted you to do. Yeah, I know we could evaluate that, but that's not the instructions. Yes, we could evaluate it by putting the 4 on the outside. What's the cubed root of 8? 2. And then 2 to the 4th would be 16. So we could evaluate it, but they didn't ask us to evaluate it. They specifically asked us to write it with rational exponents. So I would expect you to leave your answer like that, 8 to the 4/3. If you simplify it and say, oh, that's equal to 16. Okay, fine, but I need to see this on your paper to show me that you were following the instructions and knew what this meant. I must see that. This is nice, but I must at least see this so that you are following the instructions. This one, don't let the mess inside here scare you. We would just write 7x, y. The index becomes the denominator. The power becomes the numerator. And again, what mistake did I just make on purpose? Yeah, the way it's written right now, that 5/4 power only applies to the y. As if only the y was inside. No, we needed to take the whole thing to the 5/4 power. Yes, those parentheses are not optional. Some things I've seen on people's papers, I get the impression that you believe parentheses are optional. No. This is very much different than this. They do not mean the same thing. The parentheses must be there. Again, write with rational exponents. In other words, get rid of the radical sign. So we have 3, a to the 4th, b to the 3rd, all to the index becomes the denominator, the power becomes the numerator, 4/7. That's all they wanted you to do. That's the ugliest one. That's one of the odd problems in the assignment. You're going to be given the evens. I just wanted you to warn you, don't let the ugliness of this one scare you. It's the same as all the others. Just take this guy to the 4/7. You're done. Yeah, there are other things you could do to this, but we're not going to. You're done. You have followed the instructions. All you have to do is follow the instructions. Did we write this with a rational exponent instead of a radical? Yes, we did. Did we follow the instructions? Yes, we did. So please just follow the instructions. Don't torture yourself by trying to do something else. And I just saw that my phone is not plugged in. I sure hope the battery is not dead. If it is, I've got to start all over again. Okay, that's the end of part 1. We'll do part 2 next time. This is probably Wednesday that you're seeing this, and you'll get part 2 on Friday. Watch out though, the book has part 1, part 2, part 3, part 4. The book's parts have nothing to do with my parts. We just did the book's parts 1 and 2, I think, and we'll do parts 3 and 4 of the book next time, but I'm ignoring those part names. So my parts have nothing to do with the book's parts, okay? So as far as I'm concerned, this section is 2 parts. Last part coming next time. And here's your assignment for part 1. This will be due by noon on Friday, page 315, 10 through 38 even. It is if it looks to you like a short, simple assignment, you're right. It's a whole lot shorter than that old 2 through 52 assignment. I know that was kind of nasty. I should have made it shorter, sorry. But this was a nice, short, relaxing assignment. All right, and that's it. I think there's nothing on the next screen. Nope, nothing. Okay, so we are done, and I hope my phone is still alive. Oh, it is. Good. All right, goodbye.